This is Module 7, Lesson 4. We are now going to continue to work with our covalent molecules that we've been drawing to talk about polar and nonpolar molecules. Okay, here's the deal. Electrons are not always shared equally in molecules. We have talked about electronegativity before, and remember on our periodic table, our trend was that things were more electronegative up and to the right, which means that unless you're the exact same element, it's probably true that you don't have the exact same electronegativity. You have nonpolar bonds when electrons are shared equally. So if you do have two of the same element, like two nitrogens have the same electronegativity, then they're going to share them the same. Same thing goes for two H's or two O's. Most of the halogens will bond diatomically together, like Br will be Br2, I will be I2. So if you're a halogen, chances are, they'll go together like this, like F2, Br2, Cl2, like they like to be together as diatomic molecules. Then those would all be nonpolar covalent bonds because there's not a difference in electronegativities. But for a lot of our covalent compounds, it's not between two atoms of the same element. So when you have different electronegativities, electrons are not shared equally, and you have a polar bond or a polar covalent bond. The more electronegative atom is going to pull the electrons to itself more strongly, and what it does is it gets a slight negative charge. Okay, the one that's less electronegative will have a slight positive charge because it's slightly losing its electrons. Now, this is not a complete transfer, it's just kind of a partial charge. Polar molecules, have poles, and that's what poles are. Poles are extremes or opposites. So a polar molecule is one where you have a slight positive and a slight negative end. They have what's called a dipole moment. They end up with two opposite poles. We're going to look at this as we move forward. Here are some examples of polar molecules, okay? So HCl is polar, and I'm sorry, this should be a lowercase. I caught it up here. This did it in all caps, and so not everything is like I want it. Cl is more electronegative than H. On our periodic table, Cl is way over here, H is way over here. Our trend was up and to the right. Cl is in placement to be much more electronegative than H. So if we draw this out, like here's our H and here's our Cl, and they are bonded together, what this means is that electrons are going to want to gravitate over here towards the Cl more often than they go to the H. It's going to give this a slight negative charge, and it's going to give this a slight positive charge. The same thing goes for H2O. Its shape is bent. So here's our O's on it, and or here's our O and here's our H's. This is more electronegative. The electrons are going to want to hang out up here more. I'm not doing a particular number, just however many. So the O is going to end up having a slight negative charge, and these H's are going to have a slight positive. So how do we show this? Well, there's kind of three different ways. One of them is this way. It's using the Greek symbol delta. Capital delta looks like a triangle. Sometimes you see little legs on it. Lowercase delta, it's kind of like, I kind of do like I'm going to make a number 8, like start at the top, come around. Oops, it's not what I wanted to do. Start at the top, come around, but don't go up and finish it off. Just, stop right there. That's usually how I do it. We could do it this way. So if we drew it out, if we drew like we just had water right here, what we would do is we would put delta negative on the O, and we would put delta plus on our H's. And what that means is partially negative, partially positive. You could do the same thing with the HCl. You could denote slightly negative, slightly positive. That's one way. You can show it with the density of electron clouds. This is not how I'm ever going to show it in writing because I'm not going to try to draw that. You can see how this one is much darker, and the H doesn't look symmetrical. It looks like it's kind of been pulled this direction a little bit. It's lighter on this side, it's darker over here. That's what they're showing you, is that the electrons are going to kind of gravitate towards the Cl. The other way that's commonly shown is by using an arrow that points towards the more electronegative. it'll start out as a plus over the positive element and continue over the negative one. So if you're going, say what? Well, then try this, like HCl. What you could do is draw it this way, like this. It's a positive down here at the H, and it points to the Cl. So we kind of do our bonds, but showing that it's like the electrons are going to head this way, like go to the Cl. We would do the positive down here. If you did it with the H2O, then you would draw your arrows pointing towards that and put your pluses down here towards the H would be one way to do it. That means that this is more electronegative, so I know by default it would be negative. Okay, here are some other attractions between molecules that I want you to know, and then I'll show you how to determine polarity for your practice problems. So I don't know that I need to do all this for you. I think you can read and you can write things down. There are two types of these are called van der Waals. It's either German or Austrian, so pronounce this like Volkswagen, like that W. So it's van der Waals forces. There are dipole interactions and there's dispersion forces. So you can read those and you can write them down. If you have questions, ask. Then you also have hydrogen bonds. These are extremely important to life because, well, it's what holds DNA together. It explains a lot of the properties of molecules that we have in common and that we know that make up living things. And it's simply where you have an atom, a hydrogen that's covalently bonded to a very electronegative atom is weakly bonded to an unshared electron pair. So, for example, to draw this one out, like if you had water right here, we said that this has a slight negative and this has a slight positive. Well, oxygen also has some unshared electron pairs around it like this. So if we have another water molecule over here, like this, I'll turn it a different way, what can happen is this hydrogen, it has a slight positive charge, can actually weakly bond. It can kind of interact with these over here. I'll do the hydrogen bond in green. This positive can interact with these negative electrons. They like each other because they're opposites and they attract. So this one says, how you doing? And this one says, fine. And they like each other and they attract. See how that works? Okay. So, there you have it. There's hydrogen bonds. Okay. Last little bit here is about molecular properties. And this is properties of covalent compounds that are slightly different from what we've already studied. We've already said that they have lower boiling points, but there are a few anomalies of this. They're called network solids, like diamonds and silicon carbide, where their atoms are all highly bonded to each other, and they are so bonded that they are super duper strong. So network solids are kind of the exception to the rule for molecular properties. Diamonds don't melt, they vaporize at an extremely high temperature. Silicon carbide is used to sharpen steel. Diamonds are often used to cut things that are considered to be impossible to cut, like you have diamond tip drill bits and saw blades because of their unique strength. Okay. Now for your practice time, I wanted to make the point to you about determining whether or not covalent compounds are polar has a lot to do with their shapes. Okay. So remember we had the tetrahedral shape. So tetrahedral things, if you have 4 of the same atoms attached to it, they will be non-polar because there is no way for them to be pulled in any particular direction that will give it a pole. But if one of the atoms is different, so for example with tetrahedral, if we had CH4 like this would be non-polar. C is more electronegative all the way around, but you're not going to have poles. There's no opposite end. If you could replace this with a chlorine, then you would have a polar molecule. Because chlorine is more polar than everything else, it would have the dipole moment. You would end up with a slight negative on this end and a positive kind of on the opposite end of the molecule itself. Okay, pyramidal. they tend to be polar. I can't spell. They tend to be polar just purely because of their shape. Because they have a shape that's like a pyramid, it makes it exceptionally easy for one of the ends or the other to have a positive or a negative charge. So pyramidal is a good bet to be polar. If in doubt and it's a pyramid, say yes. Okay, because of just simply how they're shaped. The other option here for 3 attached atoms was triangular planar, and they tend to be nonpolar, just like tetrahedral, unless one end is different. I'm just doing the tendency, so hopefully you're listening to me and not just writing down what I'm writing up here. Triangular planar could be polar if, for example, if it was like B, H, 2, and then F. This could be polar because this is so much more electronegative than anything else on it. But if it was B with 3 Fs, then that would be nonpolar. You know, the only way that these are going to be polar is if you have something that's very different from everything else. These typically are polar. Same thing goes for bent. Bent tend to be polar because of their shape. Their shape lends them to having 2 opposite ends. So you could easily have like a negative end and a positive end. Linear works like triangular planar and like tetrahedral. It tends to be nonpolar unless you have one end that is really different from everything else. I personally think the easiest way to do this and not get screwed up is to go back to your shapes and then to look at it and go, well, you know, is it kind of evenly spread out? Do I have everything the same around it? And you can memorize, like I just said, pyramidal and bent tend to be polar, linear, triangular, planar, and tetrahedral. You need to look at, is it all of the same attached atom? If it is, it's nonpolar, and if something is drastically different, then it's going to be polar, and kind of to think it through. Okay, this is something again on the final exam that they could ask you to pick the polar element, but they're not going to show you shapes. You're going to be left to figure out the Lewis structure, the Vesper shape, and then the polarity of it. Now, you are going back to the same sheet that we have worked on for the 3rd time now. You're going back, you are working on the polarity column this time. No need to print it for the 3rd time, just simply decide if it is polar or not. You should need to use these 2 things that you have done so far to figure out the 3rd. All right, so get to practice.